In this video, we are going to go over the examples from section 2.2 in linear algebra. And for example number 1, we want to show that these matrices are inverses. The way to do that is, if they are inverses, we would have the original matrix times its inverse is supposed to be equal to the identity matrix. If we do it with using right multiplication or left multiplication. So A inverse times A is equal to the identity matrix. The identity matrix for a 2 by 2 matrix looks like this. One, zero, zero, one. So as long as we obtain that, there would be inverses. So we need to multiply A times C and C times A to check it. A times C, this would take A of 2, 5, negative 3, negative 7, times C of negative 7, negative 5, 3, 2. Okay. So if we start multiplying, 2 times negative 7, that'll be negative 14. 5 times 3 is 15. Negative 14 plus 15, this would be a 1. For the next entry in that row, 2 times negative 5 and 5 times 2. That'll make negative 10 and positive 10. Adding those makes 0. Negative 3 times negative 7, so that'd be positive 21. Plus negative 7 times 3 is negative 21. Positive 21 plus negative 21 will give us a value of 0. And then negative 3 times negative 5, that'd be positive 15. Plus negative 7 times 2, that's negative 14. So 15 plus 14 will give ourselves a value of 1. Okay. So far it appears like C is the inverse of A. Now we need to try the other direction. C times A. Again, just to make sure that they were inverses. So negative 7, negative 5, 3, 2, and that'll be times 2, 5, negative 3, negative 7. Again, we want the 2 by 2 identity matrix, if these are indeed inverses. So negative 7 times 2 will be negative 14 plus negative 5 times negative 3, it's positive 15. Negative 14 plus 15 will give us a value of 1. Negative 7 times 5, that'd be negative 35, plus negative 5 times negative 7 is positive 35. Adding those two gives us a 0. 3 times 2 is 6. 2 times negative 3 is negative 6. Adding those is also a 0. And then finally, 3 times 5 is 15. 2 times negative 7 is negative 14. Adding them gives us a 1. So that means A and C then are indeed inverses. And we can label C to be the inverse of A. And we can also label A to be the inverse of C. Same spiel. And we could show that in SCS if we wanted to. I'm not going to do so in this, just because we've shown it on here. It's going to give us the same result. But we can multiply these two matrices in SAS, and we would obtain the same identity matrix. Now, if we want to find the inverse, of a matrix, right, and we have, a very special way that we could do it. We need to take, this is 1 divided by, if we were to label a matrix like that, a 2 by 2 matrix like this as A, B, C, D, this would be 1 divided by AD minus BC times, this would be the matrix D, negative B, negative C, A. That is the specific definition of what the inverse of a 2 by 2 matrix is. So in our case, AD minus BC, this would be 18 minus 20 times, this would be switching 3 and 6, this would be 6 here, 3 down here, this would be a negative 4 and a negative 5. 18 minus 20 is negative 2, so this is negative 1 half times 6, negative 4, negative 5, and 3. So, doing so now, we can now multiply every entry in the matrix by this negative 1 half. This would give us values of, let's see, negative 3, 2, 5 halves, and then negative 3 halves. We could also do this in SAS if we wanted to, by first doing the procedure, so proc IML. We want to define our matrix A to be as what we have on the screen here of the entries 3, 4, comma, 5, 6. And we want to do the inverse of A, so this would be INV of A, for inverse of A. And then we want to print whatever that inverse is. Doing this will give us our matrix as what we just have here. Negative 3, 2, 2.5, and negative 1.5, which I just wrote decimals instead of fractions. And depending on the circumstances, you might want the decimals as opposed to the fractions. But in this particular case, that's what that makes. For example number 3. Now this is the type of question where doing this out by hand will probably take a long time. So this I'm going to specifically do in SAS on here, just to show how that would work. But for this, a horizontal elastic beam is supported at each end and is subjected to forces at points 1, 2, and 3. Let the vector F in R3 list the forces at these points, and let the vector Y in R3 list the amounts of deflection movement of the means at the 3 points. By Hooke's law, we have the vector Y is equal to the matrix D times the vector F, with the matrix D being the flexibility matrix. Its inverse would specifically be the stiffness matrix. And we let D here be this lovely big matrix here. 0.006, 0.0012, 0.003 for the first row. The second row is 0.005, 0.0048, and 0.0014. The last row is 0.003, 0.006, and 0.0012. The vector F is 30, 50, and 10. So for this, we want to multiply these two. So, specifically speaking, we are doing this operation here. And let me just rewrite out D very quickly, so we could see what this looks like. As you can see, just writing these out takes its own length of time. Taking that entire matrix D times the vector F of 30, 50, and 10. And then you have to do each one of these separately to obtain our answer for Y. But if we wanted to do inside of SAS, which I would recommend doing so in a case like this, we would need to copy that exact matrix in SAS. So 0.006, 0.0012, and 0.003 for that first row, 0.005, 0.0048, and 0.0014 for the second row, and the third row of 0.003, 0.006, and 0.0012. And then we want to define that vector f. We want to define the vector f then as that particular vector. So this should be listed out as 30, 50, and 10. And then to show the multiplication, we're just going to multiply the matrix. I'll call this D so we could actually match the problem. D times F. So D times F. And then we should obtain our answer. Doing so, if I click the right button, doing so gives us an error, which let's just see why that is still. Oh, I forgot to put a semicolon here. That should now give us our answer of 0.27, 0.254, and 0.402. For our solution vector, for this particular case, which in this case would be the amount of deflection or movement of the means at those 3 points. Now for example 4, we could use the inverse matrix obtained from example 2 to solve the linear system of 3x sub 1 plus 4x sub 2 is equal to 3, 5x sub 1 plus 6x sub 2 is equal to 7. And to recall, that inverse matrix was this. -3, 2, 5 halves, and -3 halves. So to solve for this, our vector x would be this inverse matrix that I just wrote. So -3, 2, 5 halves, and -3 halves, times that solution vector here of 3, 7. And if we want to multiply these, -9 and 14, this will give us a value of 5, and then 15 halves plus -21 halves will give us a reduced value of -3. So our vector x is 5, -3, which we could also do in SAS if we wanted to. For number 5, we have 3 vectors, e sub 1 being 1, 0, 0, 0, 1, 0, -4, 0, 1. E sub 2 of 0, 1, 0, 1, 0, 0, and 0, 0, 1. And then E sub 3 of 1, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 5. If we want A, B, C, D, E, F, G, H, I, we want to compute E sub 1 times A. So this first row times this column just gives us A. Then this row times this column gives us B. And this row times this column gives us C. Likewise, this row times this column will give us D. This row times this column gives us E. And this row times this column gives us F. Now this row times this column gives us -4 times A plus G. This row times this column gives us -4B plus H. And this row times this column gives us negative 4c plus I, which, essentially speaking, is the same thing as the elementary row operation. The elementary row operation of taking negative 4 times the first row and adding it to the third row. Then for e sub 2 times a, this row times this column would give us a value of d. This row times this column gives us e. And then this row times this column gives us f. This row times this column gives us a. This row times this column gives us b. And then this row times this column gives us c. And then likewise for the last row, 0, 0, 1 times this column gives us g, then h, and then I. And that is a very bad looking h. This is the same thing as the elementary row operation of interchanging the first and second rows. Again, that's a very bad R. And then the third one of e sub 3 times a. I'm going to just very quickly add a space in here for more room. E sub 3 times a. This would be this row times this column. This would give us a, b, and c. This row times this column gives us d, and then e, and then f. And then finally, this row times this column will give us 5 times g, then 5 times h, and then 5 times I. This is the same thing as 5 times the third row. For our next example, we want to find the inverse of e here, with e being 1, 0, 0, 0, 1, 0, and then negative 4, 0, 1. And as I wrote there, we want to find its inverse. And when it comes to doing this, right, in order for us to find the inverse, we only need to do one type of elementary row operation here in order for us to get the identity matrix. That being, we take 4 times the first row, add it to the third row, to get that identity matrix. So, the inverse of E takes almost the same exact matrix, so 1, 0, 0, 0, 1, 0, just this negative 4 here is going to be a positive 4. Positive 4, 0, and 1. As opposed to negative. That's the only difference. And we could see that's the case if we were to take... I'll just do one of these out. E times the inverse of E. This row times this column gives us 1. Then 0, 0. And this row times this column gives us 0, 1, then 0. This row times this column now gives us the 4 plus negative 4. This would be 0. And then this times this would give us 0 and then 1. And if we did it the other way, we'd get the same exact answer as well. For the very last example here, we want to find the inverse of A being 0, 1, 0, 1, 0, 3, and then 4, negative 3, and then 8. If we were to go through the whole process of finding this, we would need to solve this, which would take the matrix A, and then from the educated matrix here of A with the inverse. So we would be actually solving this. And I'll write what it is. As you can imagine, there will be a lot of steps since we would need to obtain the identity matrix on the left. We would have a matrix that looks like this, right? With the educated matrix. We want this left side here to be the identity matrix, which is what I mean by solving it. And then the inverse then would be on this right side. And as you can imagine, that's a whole lot of steps. We could do instead of SAS. So let me change this by putting in A first. So 0, 1, 0, 1, 0, 3, and then 4, negative 3, and 8. And I want x here to be the inverse of A. And then we can print it. Doing this will give us that is not our inverse. I called this D instead of A. That might be helpful if I use the same matrix. This would give us this particular matrix down here, if we were to do this out. Which again, as you can imagine, will be a whole lot of steps since we want the inverse matrix. So we need to use that Gauss-Jordan elimination method. But this gave us here of 2.25. So this was 5. For 2.25, that's now 5. So 2.25, and this is supposed to be a 9/4, a negative 2, 3/4, 1, 0, 0, and then negative 3/4, 1. And for that final entry, we have ourselves negative 1/4. Alright, so if we were to do the math out by hand, again, it would take a rather long amount of time. We would obtain this inverse here of 9/4, negative 2, 3/4, 1, 0, 0, negative 3/4, 1, negative 1/4. Let me know if you have any questions or concerns. Thank you.